Today I'm going to talk to you about some of my recent work on the mass dependence of satellite quenching in the local group. And so I'd like to begin by just kind of examining the discrepancy between models of quenching and what we see in observations. And so what we have here is a plot from Hirschmann et al. 2014, and this is showing the quench fraction as a function of stellar mass, but this plot is a little bit busy, and so I'd like to just focus in or draw your attention to the what we see here in the green. And so the models for satellites end up drastically overproducing the quench fraction, and this problem gets particularly noticeable as you move down in stellar mass. And so the models are the green line, which you see end up at somewhere about 75% quench fraction, while the observations trend downward, ending somewhere around 30%. This discrepancy can kind of help motivate us taking a closer look at what's actually happening between the dwarf galaxies and their host environments. I think it's also worth noting that the models predict somewhat uniform quenching across maybe 2 decks in this lower range in stellar mass. And this uniformly efficient quenching is really just not seen in the observations. And so here we have a plot showing the satellite quenching efficiency as a function of stellar mass for 3 different groups who've done this observationally using SDSS. And you can see across a similar stellar mass range as we showed previously, the observations indicate that quenching is uniformly inefficient across this range. Now we can use these relatively low quenching efficiencies and kind of play a little game. We can compare the subhalo populations in N-body simulations and infer a typical quenching timescale relative to infall that would then reproduce this observed quench fraction. And so when we do that, we get this result where we have quenching timescale plotted as a function of stellar mass. And you can see that these relatively low quenching efficiencies in the high mass regime end up leading to long quenching timescales. And this is particularly noticeable at about 10 to the 9 in stellar mass, where the quenching timescales get up to about 7 to 9 gigayears. Now, these previous works have really pushed the limits of SDSS. And so I'm interested in looking at satellites that are lower in stellar mass. And so in order to do this in a consistent manner, we're going to have to kind of modify our approach. And so we're going to look into the local universe, specifically the local group, and do this in a hopefully consistent manner. And so this is the same figure as I showed previously, except we now have a local group point on there. It's somewhat comforting that the local group in the same stellar mass bin as was shown previously is consistent with the global population. And when we now push to lower satellite stellar mass, we see an abrupt change in the quenching efficiencies. And in order to kind of understand what's going on here, we're going to play the same game, but instead of comparing to large N-body simulations, these local group points are better compared to local group simulations. And specifically, I utilized the Elvis suite of simulations, which is particularly useful for this type of analysis because, due to its relatively high resolution, and they model both the M31 and the Milky Way together, as you can see here. And so when I played this game, these high quenching efficiencies seen at low satellite stellar mass lead to relatively or quite low quenching timescales. And I think it's worth spending a couple moments looking at this figure. This figure is, I think, somewhat remarkable in that we've managed to quantify the relevant quenching timescales over about 5 decks in stellar mass. And we can use this, or we can use these trends that we observe in the quenching timescale to then try and learn something about the physical mechanisms that are actually acting on these satellites and ultimately shutting down star formation. So if we begin first at the higher mass end, this high mass end, basically you see exceptionally high or relatively high quenching timescales. And these high quenching timescales are really indicative, or there's really only one process that can lead to such high quenching timescales, and that's starvation. And so if starvation is acting in this regime, then the quenching timescale should scale as the depletion timescale, and the depletion timescale is, yes? Oh, thank you. Sorry. And the depletion timescale is kind of to first order the total mass available for star formation divided by the star formation rate. Any other proposed mechanism that could be acting in these environments would generally act to reduce the fuel available for star formation and thereby reduce the quenching timescales. So starvation is really the only mechanism that can get us up to these high quenching timescales that we observe. So typically, H2 is the fuel for star formation. The depletion timescales for H2 that were recently measured by Baselli et al. Are in conflict with what we see in this quenching timescale. Baselli et al. Measured depletion timescales of H2 gas in this high mass regime of about a gigayear. So galaxies deplete their H2 exceptionally quickly, and that we just can't get up to the quenching timescales that we see here. However, if we include H1 as an additional source of fuel for star formation, we see the following. And so here we have plotted the depletion timescales as a function of stellar mass for 4 different models that utilize both H2 and H1 as the fuel for star formation. And if the high mass trend is indeed consistent with starvation, then these depletion timescales should match up nicely with our measured quenching timescales. And kind of lo and behold, they do. And so I would argue that this picture, where starvation is the dominant mechanism of the high mass regime, is consistent if H2 plus H1 is the fuel for star formation. Additional evidence to that, or that supports that, is the fact that the quenching timescales in this regime seem to be relatively independent of host halo mass, which is again indicative of starvation. Now, if we move to the lower mass end and try and explain the trend there, we run into problems with this starvation picture, and that's generally because these low mass objects in the field are gas rich, and so those would lead to quenching timescales that would drastically exceed what we see in this high mass end. And so we need another mechanism that would act to dramatically reduce the quenching timescales we observe. Ram pressure seems like a likely candidate. Ram pressure is going to act to reduce some of the fuel, or reduce the fuel for star formation, thereby lowering the quenching timescales. And our group has done some initial kind of back-of-the-envelope calculations, and ram pressure stripping is certainly more effective in this lower satellite stellar mass range than in the higher satellite stellar mass range, which is good. However, it should be noted that the magnitude of that effect is still somewhat uncertain. And I think ultimately more work is required to really get a handle on whether or not ram pressure stripping is effective enough to get us down from these high 8 to 10 gigayear quenching timescales down to 1 to 2 gigayears that we observe locally. So this is my summary slide. Just a quick kind of the takeaway points is that the low mass satellites in the local group are almost uniformly quenched. This high quench fraction requires an exceptionally low quenching timescale, and the turnover, when we place these low mass quenching timescales in the context of the higher mass regime, the turnover in this timescale is really suggestive of another physical mechanism taking over outside of starvation. Thank you very much.
Thank you for finishing it. Joel.
Very nice talk, very clear. At the end, though, I'm a little uncertain what you mean by ram pressure stripping. Okay. What people usually mean is that the gas in the central part of the galaxy gets stripped out because it's passing through some fairly dense gas in the environment of the big galaxy. However, as simulations by Anorbe et al. And practically every other group that's done these low-mass galaxies have found, they're very episodic, with bursts that drive gas out from the center of the galaxy. Now, in the environment of a massive galaxy, you don't have to get too close to the massive galaxy for that gas that's been driven out of the center to get stripped off as the satellite moves through. I'm not sure if that's what you meant by ram pressure stripping, because it's not the usual picture, but that's probably what's going on in these stripped galaxies. And a way to test that is to look at what the time scale is as a function of galactocentric distance, that is the distance from the central galaxy. We know that it's not effective if you're far away.
Yeah, that's certainly true. I think our initial analysis of ram pressure is that we wanted to strip out the H1 from these objects. And initially it doesn't work basically, and we made a pretty aggressive assumption of what the Milky Way hot gas halo is, which is ultimately the stripping medium, and there's a lot of uncertainty to how dense that is and to what extent that is in the Milky Way.
Feedback, and that's basically what I'm saying.
Right, exactly. And so the next step in our analysis is to ultimately include stellar feedback, which would help to puff up the ISM of these objects and make them easy for stripping, yeah. We think that that's going to be necessary for this to be as effective as we think it should be.
I agree.
Yeah, thank you.
Indeed.
So concerning quenching timescale versus depletion timescale, within the depletion timescale, you reduce the gas mass by a factor of E, because the m gas over dt is m gas over tau. Yeah. Which means after depletion timescales, you didn't run out of gas. You're still forming stars.
Right.
So actually, you need to be a little more careful. You can run over several depletion timescales and have star formation. It's just not, you need to define quenching somehow. Let's say you reduce the gas mass by a factor 20 or 50, and that tells you how many depletion timescale you need to go down to this final mass. So it's a little uncertain what you actually did, and whether the gas we have is already enough to go into the Green Valley and through the Green Valley over 5 depletion timescale might be correct, might still be okay.
So you're saying in the low mass end where the depletion timescale is short?
Yeah, we know, because you said you need H1 just to keep going for 5 gigayears, without infall, but I say you don't get rid of all the gas in the depletion time. It takes forever actually, because you have an exponential decline in the gas mass if star formation rate is always proportional to the gas mass. So that you actually have star formation all the way to infinity if you want. Just depends on what you define as reasonable star formation and what is for you a quiescent galaxy.
So if I understand you think we should be careful with what we define as quench as to whether or not they've truly stopped forming stars? Yeah. Am I understanding that correctly? No, well, okay. I guess for the sake of time, just quickly, when we looked at quench objects in relation to how many stars they've actually formed, we've looked at like the Y star formation histories, for example, and we've looked at the distribution of at what point in time did they form a given fraction of their stars. And Dan Wise and our group basically assume that once they formed about 90% of their stars, they're effectively quenched. And so they might still have a few small episodes of star formation, but on the whole, they're effectively done with star formation in any appreciable manner.
I'll throw Chair's perspective. I'll throw in. It's a little better than you said in that we know that once you transition from having significant H2 to not having significant H2, your depletion time goes up by a factor of 50. So it's not like your depletion time is constant. You can deplete down to the point where you transition from molecule rich to molecule poor, and then your star formation rate will drop like a rock.